We're going to start by looking at Biot-Savart's law. And so recall, as I stated at the end of the previous video, this is going to be more similar to Coulomb's law for our static charges. Ultimately, what we're interested in finding here is our magnetic field intensity H due to some constant current. And so to keep things simple, let's just start with some filament that has some current I. So I've drawn this filament in blue, and so you can see the current is sort of going in this direction, and our filament is extending beyond where we've drawn it here. So that's the dashed lines on either end. And so we're interested in the magnetic field intensity at some point P. And so what we're going to do, similar to when we looked at our Coulomb's law, is we're going to just consider some differential component. So we're going to consider a DH, a differential magnetic field intensity. Now, of course, that's going to have a direction because our H is a vector quantity. And so in order to determine that direction, we can use our right-hand rule. So our right-hand rule, to do that, what we're going to do is we're going to place our thumb in the direction of the current. And of course, this is the thumb of our right hand. So thumb in direction of current. And then we're going to curl our fingers. And that's going to give us the direction of H. So in this case, we have our thumb pointing in this direction, and we curl our fingers and we see it's coming around and going sort of into the page on the side of the wire or this filament that P is on. And so a refresher on some of this notation that you might have seen when dealing with physics is that once we enter this third dimension, it's useful to have some notation to indicate whether fields are coming out of the page or into the page. So we're typically going to represent out of the page with a circle with a dot in the middle. So this is going to be outward. And if we have something going inward, it looks something like this. So a circle with an X in the middle. So this is going to be going into the page. So in this case, we could say at point P, we have some DH which is going into the page. So we draw a circle with the X in the middle. And so a good sort of way to help you remember this notation, if you're not already familiar with it, is we can think about an arrow. So if the arrow is coming at us or out of the page, we're going to be seeing the point of the arrow. And if the arrow is going into the page, then we're going to be seeing something that looks like this. Obviously not 100% accurate, but a nice little analogy to help us remember that notation. Okay, so we know the direction of our H. So now what we're going to do is figure out the Biot-Savart's law in order to get a more exact expression. And so before I do that, let me kind of set it up by considering a couple things in this drawing. So just like with Coulomb's law, when we consider some differential charge, let's consider some differential current in some region of this filament. So let's say, for instance, right here, we're going to consider some dl of our filament. So this is some dl right here, which has some differential current. And we're going to draw a line from that differential segment to our point of interest. So we have something like that. And we're going to call this our R vector. And let's also define some angle made by that R vector and the path of our current. So we're going to have some vector alpha here. So what our Biot-Savart's law states, and we're just going to put it in equation form. It's written out fully on page 298 in the text. So let me go ahead and put that here. So 298 in the text. But we're just going to write it in terms of the equation because I think that's a little more straightforward. So what our Biot-Savart's law says is that the magnitude of that differential magnetic field intensity dH, so the magnitude of this guy, is proportional to the differential current. So our differential current is going to be I times that differential length, dl. So again, this is our differential current in that little segment dl. It's also proportional to sine of that angle alpha, which is made between our R vector and the path of the current. And it's inversely proportional to the square of that distance between our point of observation and the filament. So we have divided by R squared. So we can tweak this a little bit, and again, as I mentioned in the previous video, you can look at a full derivation in a later section in the chapter, but we're not going to cover it. But basically, if we just add a proportionality constant and use the definition of cross product, we can get our full equation for dH. So adding a constant of proportionality, and so this is going to be similar to how we added what we earlier called our capital K value with our electrostatic fields. So we had that factor that depended on pi and our permittivity. So adding constant of proportionality, and we're going to be using the definition of cross product because we noticed we had that sign of alpha in there. And so we know that our cross product, when we do that on two vectors, results in the magnitudes times the sign of the angle between the vectors. And we can say that our differential magnetic field intensity, dH, is going to be equal to, we have I dl cross unit vector in the r direction divided by 4 pi times r squared. And so as we saw earlier with various other types of equations that had a similar form, we can rewrite that unit vector and we can say this is also equal to I dl cross r, and now we just added another magnitude term in the denominator, so instead of 4 pi r squared, we now have 4 pi r cubed in the denominator. And so this is going to be the basis for using our Biot-Savart's law, and in the next video we're going to see how we can use this basic dH and talk about various current configurations.